Hi, recently I took a physics test and I thought I'd like to share one of the questions from the test. This particular question was the topic of this particular question was about patterns of field in space, with a lot of Gauss's law of equation involved in it. So in this particular question, we have a cylinder with radius r and the height L, and here we have a point A with distance d away from the midpoint of the cylinder, and we are given that the d distance is greatly small compared to the height L, and the total charge of the cylinder is said to be Q, and its charge is evenly distributed throughout its volume. So the first part of the question, it asks us to find the density of the charge. So basically, the density of the charge is the total charge divided by the volume of the shape. So we have the volume so we can find the volume of the cylinder by multiplying the area of the base times the height of the cylinder, which is L. So we have here the volume equals pi r squared. Hold on, let me zoom it up. So we have the volume of the cylinder equal to pi times radius r squared times the height L. After that, the next step is just dividing the volume from its charge, which is Q, the total charge, divided by the volume, which is pi r squared times L. So that answers the first part of the question. And the second part of the question asks us to imagine imaginary Gaussian surface, which is cylindrically shaped, inside the original cylinder. Which has surface with radius d and height L, which is same as the original cylinder's height. And then it asks us to find the total electric flux of the imaginary Gaussian surface. So for that, so to solve the second part of this question, we have to use the Gauss's law, which is electric flux is equal to the total charge divided by the epsilon naught. So charge of the inner cylinder with radius d is that it can be said that from the previous question, we have the density of the charge, which is Q, density of the charge, which is Q divided by pi r squared L. So for this particular question, we can multiply the volume of the inner cylinder, which is the imaginary Gaussian surface, times the density of the charge, which is Q over pi r squared L. So for this equation, we can simplify to Q times d squared over r squared. And that corresponds to the total charge inside. So to get the total electric flux, we can simply divide the total charge divided by the epsilon naught. So Q times d squared over epsilon naught times r squared is the answer for this second problem here. The third problem of this question asks us to find the magnitude of electric field at location A in the cylinder. So in this diagram, we have point A separated by distance d from the midpoint of the cylinder. So for this third problem, we also have to use Gauss's law again. So according to the Gauss's law, it states that the electric field times the area surface is equal to Q over epsilon naught, which is the total flux of the imaginary Gaussian surface, which we found from solving the second part of the question. So in order to get the total magnitude of the electric field at location A in the cylinder, we have to divide the total flux by the electric field here. The area of the surface. So area of the surface of the cylinder, like the imaginary Gaussian surface, we can simplify that to 2 times d times pi times the height L. 2d pi here is equivalent to the circumference of the imaginary Gaussian surface, which is in the form of cylinder, and L is the area of the height of the imaginary Gaussian surface. So what that means is, what that area represents is the side area of the cylinder. We can simply neglect the area of the top and bottom plate of this imaginary Gaussian surface, because the original problem says that the distance d is infinitesimally small compared to the length of height. So the area of the top and bottom surface of the imaginary Gaussian cylinder should be very small. So we can simply neglect that in our equation. So in order to find the electric field, we have to first we need the Gaussian, we need the electric flux, and we can simply divide the area of the surface from both sides. So there's the equation we here. That's the total electric flux. That's the total electric flux of the Gaussian surface that we got from the previous part of the problem, and we are just dividing it by the area of the surface here, and by solving that form, it simplifies to q times d over 2 pi L E epsilon naught r squared. That is the magnitude of the electric field at location A in the cylinder. Location A. So that answers the part 3 of the question, and I'll try to come back to you. I'll try to make another video of the question of the test after I take the next test on physics 2. So thank you for watching, and see you next time. Bye.